Welcome back. This is block 2. And here what we're going to look, it's like multinomial classifications when we have more than one class, okay, more than two classes, sorry. Okay? And basically we're going to look at the multinomial logit, random utility model, maximum likelihood estimation, and penalized likelihood. Okay? The same references as before. So we have more than two unordered options. So for instance, we have to decide what we're going to have for lunch. We can have pasta, choice 0, sandwich, choice 1, or salad, choice 2. Or we have also ordered response where designated values are not arbitrary. For instance, credit rating can be 0, 1, 2, 3, 4, 5, 6, and 6 being better than 0. Okay? Basically here we are going to focus on nominal responses which are unordered. Okay? So that the binary logit is that expression here on the top, right? What we are going to look at is the multinomial logit. So now we have like j classes plus the baseline one, 0. Okay? So the probability of yi equal to j, choice j, given x, will be the exponential of xy, and now we have a beta, a different beta for each class, each one of the j classes. Okay? So this will be the exponential of x prime beta j divided by 1 plus the sum of all the other exponentials. And the baseline probability will be 1 minus all this term here, and this will be equal to 1 over 1 plus the sum of x beta, the exponential of x beta. Okay? And note that, as I mentioned, beta j depends on the choice j, okay? And the beta naught for the class, the beta for the baseline class is 0, okay? And important thing, probabilities should sum to 1. That's why we wrote the probabilities the way we did, okay? And if j equal to 1, we get exactly the binary logit, okay? And so how can we write this in terms of this random utility model? Suppose there are 3 possible investments. Like 0 is fixed income, 1 assets, 2 derivatives. Okay? And you have an utility for each investment. So fixed income is the baseline one. So your utility will be mu 0 plus epsilon 0. Okay? And for assets, you have an utility 1, that's mu 1 plus epsilon 1. And derivatives, same reasoning, u2 be mu 2 plus epsilon 2. Okay, so you have like the utility function for each one of the investments. Okay, so we can define the probability of investing in fixed income is the probability of the utility of the fixed income being larger than the other two utility functions of the other two investments. Okay, and accordingly we can define the probability of investing in assets with the same reasoning. Is going to be the probability of the utility function of assets being larger than the other two utilities, and the same thing for derivatives. Okay, hope it's clear. Okay. So now let's assume that these 3 epsilons, that's the uncertainty here. Okay, so this is kind of the uncertainty that we have on our utility. So it's like the random component of the model. Okay, so it's like unobserved effects or like uncertainty in general that we have. Okay? And we are going to model it as a type 1 extreme value distribution. So you may think, well, what? Yeah, but that's it. And this is a very neat probability distribution function because we are going to get the multinomial logit from it. Okay, so it's very convenient. So this extreme value distribution, the g function will be exponential of minus the exponential of minus epsilon, and the derivative is also displayed on your slide. Okay, so the probability of choice 1 is given, okay, by the probability of epsilon 1 plus mu 1 minus mu naught being larger than epsilon naught, and epsilon 1 plus mu 1 minus mu 2 larger than epsilon 2. So we can write this joint probability, okay, as an integral here. And if we solve this integral, well, look what we get. Exactly the multinomial logit, okay? We can do this we did that for y equals to 1, we can do for y equals to 0 and y equals to 2, and we get exactly the multinomial logit. So this is kind of very convenient because we derive the multinomial logit from first principles, okay? So if we set the mu naught, like the baseline utility for fixed income and being equal to 0, and we define the other mu's as linear functions, then we have exactly the multinomial logit, okay? We can also compute the partial effects. It's more complicated, so the derivative of the probability of choice J with respect to a covariate H is given by this expression. It's not really difficult to derive, it's just boring, it's just simple algebra. You have to take the derivatives and play around with all these exponentials, and you get this expression, and it's closed formula. You can compute once you have the formula, okay? And so this is the partial effect. So one thing that's interesting is that the sign of the partial effect is not determined by beta, but it will be determined by the difference between the beta and this ratio here. And if this ratio is larger than beta, if beta is positive, we are going to have a partial effect that's negative, even if beta is positive. Okay? But if we look at the relative probabilities, then this is just the exponential of x beta j if we compare with the baseline. Okay? And if we take the derivatives of this quantity here, like the relative probabilities with respect to the baseline, then we get something that's similar to the logit partial effect. Okay? And the log odds ratio will also depend on x and the differences of the betas between the two classes that we are considering. Okay, so we can also compute the probability of me choosing alternative J1, okay, given y equals to J1 or J2 and x. Okay? And that's exactly a logit model. So what does it mean by this? How can I choose J1 conditional on y being equal to J1? Imagine that you have like multiple choices, right? You have like 10 classes that you can choose. But I'm restricting your choices to only two possibilities, J1 or J2. So you can only choose between J1 and J2, although you have like multiple ones. Okay? And I want to know the probability of you picking J1 once you have just two possibilities, J1 or J2. And this turns out to be just a logit model where the parameter of the logit is the differences between the two betas from the multinomial model. Okay, so like we can, if we restrict the multiple choices to two choices, we can derive the logit from the multinomial logit. Okay, and that's exactly what's said on the slide. Okay. How we estimate these models? Again, maximum likelihood now with a multinomial distribution. So the log likelihood of the individual I is given by this expression, and so we basically estimate beta by minimizing the sum, the negative sum over all of the individuals of this log f. Okay, and as before, we can do penalized likelihood by including a penalty, so we can do this in high dimensions. Okay, as well. Okay, so this is our block 2. See you on block 3.